Okay, so the next, basically the next illustration that we have here is, suppose that you have a function, for example, f of x is equal to sine x, a trigonometric function. We want to find the limit of f of x when x tends to pi by 2. Now, first of all, basically, as long as you're finding the limit of a function using the method of getting closer from right and left to this number a, you do need to, of course, for example, let's say that you have the limit of, for example, x squared as x tends to 2, for example. You want to find the limit of this function as x tends to 2. You need to understand what this number 2 represents, and then you can get closer to it, meaning that in the case of this function, you understand that basically this number over here is, this is a real number line, and this is 0, and this is 1 and 2, and then you can, and this is, for example, the number 3, and this is 1, and so we want to get closer and closer from right and left to this number. And you know what this number represents, you know what that is, so you can get closer to it. For example, you can try for example, you can try basically all of these values as, for example, 2.1 and then for example 2.05, and then you can go all the way up to 2.005 and 2.0005 and so on and so forth, and get closer to this number. On the other side, you can basically try all of these values, for example 1.9 and then 1.99 and then 1.999, and then get closer and closer to this number. But if you don't understand what this number is, or what this number represents, or what this number actually really means, there is no way to get closer to it. For example, suppose that you didn't know, for example, suppose that there is a number plus 2 plus 3i, for example. 2 plus 3i, this is a complex number. And you want to get closer to this number. Now, I'm assuming that you don't understand complex numbers as well as you understand the real numbers. And this number has this imaginary part. This has this imaginary part, and that might make it even impossible for you to imagine, or to imagine in your mind where this number is, on which line or where. So then, since you cannot think about it, you will not be able to get closer to it or even get farther away from it. So now the same thing applies here. You want to find the limit of sine x as x tends to pi by 2. Many people do not really understand what this pi by 2 represents. They just know that, for example, we have basically the unit circle over here, and then the units on the unit circle, this is 0, this is 90 degrees, this is 180 degrees, and this is 270 degrees, and this is 360 degrees, and then this, basically these angles are in degrees, these angles are in radians. These angles are in radians, meaning that, for example, 0, and then you have pi by 2 over here. Here you have pi, here you have 3 pi by 2, and here you have 2 pi. And here you have 2 pi. So in order to understand this number, you need to know a little bit about the circle and about the radian, about the radian angle definition. So basically, as it turns out, if you have a circle over here, suppose that you have this circle over here, and I can select the border. I want to draw a circle over here. So basically this curved path, which is basically the circle itself, I'm not saying around the circle, because the circle is actually this only this curved path, which you can for example start from here and then go around this curved path, and then you can come to the same point over here. So this is basically the circle, and that path is called the circumference. Is called the circumference of the circle. It's called the circumference of the circle. Now, what mathematicians have found about circles any circle of any size is that basically any circle that you might have is basically you have this circle over here, and this is this over here is the radius of the circle, and this distance over here is basically 2 times r, which is basically the diameter of your circle. And the circumference of the circle is also denoted by c. Now, what they have found is that basically they have found that the ratio of the circumference of this circle by the diameter is in the case of any circle of any size that you might imagine, that you might draw on a piece of paper, it's going to be equal to some number which is approximately equal to 3.14, meaning that the ratio of the circumference of any circle to the diameter of the same circle is going to be this ratio, which is 3.14. Now, you can make your circle way bigger or way smaller. In any case, that ratio is going to remain the same, 3.14. And of course, this number is not just 3.14, it just keeps going indefinitely, meaning that pi is going to be, for example, to so many decimal places would be 3.1415926535898. And of course, you can just keep generating more and more decimal places for pi. You can do that. So then basically what they have done, so what mathematicians have done is that they have taken this number as basically the number 3.1415 and whatever that was, 14159265, basically 9265, and so on and so forth. They have called this number pi. So basically pi is this number. So instead of an approximation, I can write this ratio is exactly equal to pi. Pi being this number over here. And in most cases, basically, when we solve problems, we take pi as 22 by 7, because this is a ratio which to at least, I think, which to 2 decimal places is equal to the actual value of pi. If you take 22 divided by 7, you will get 3.14 142857. This is 3.1415. So all the way up to 2 decimal places, this ratio is basically correct. So you can use it in solving problems. You can just take pi as 22/7, and then you get only 2 decimal places precision in your calculation. So now what happens here is that now C that the ratio of C and D in any circle is equal to pi, meaning that, and D being basically 2 times the radius of the circle, you can write C divided by 2r is equal to pi, or you can write C is equal to 2 pi r, meaning that the circumference of the circle is 2 times the number pi times the radius of the circle. That way you can calculate the circumference of any circle, the length of the circumference of any circle. So that is basically all about the number pi. Now, as far as the angles are concerned, basically what they have done, what mathematicians have done, is that they have basically taken, well, I suppose that's the way that they have done it. Otherwise, I don't know. That's how I would do it, for example. So you could take a circle, and they have basically, well, you could take a circle and then you can basically divide the circle into 4 completely equal quadrants. So this is the first quadrant, the second, the third, and the fourth. So you have 4 quadrants over here, and now you have to pick a number, and of course the way that they have picked this number, this has historical basically backgrounds, and this number has come from other places, like, I don't know, like many, even thousands of years ago. This number has been, they have chosen the number for whatever reason, they have chosen the number to be 360. So you say 360 divided by 2 is equal to 180, and 180 divided by 2 is equal to 90. So the number is divisible by 4, and you would get no problem there. So now they have taken this, they have taken a number 360, and so if you imagine that basically you take the whole circumference of the circle, and of course it's possible to divide the whole circumference of any circle into 360 equal distances, meaning that, for example, 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. All the equal distances from here all the way up to here being 90, and then another 90, and then another 90, and then another 90, and then the sum of all of them becomes 360, because 90 times 4 is equal to 360. Now, so each of these equal distances has been called 1 degree. So that means that if you start from this quadrant and go all the way up to this line, meaning that from the beginning all the way up to the end of the first quadrant, that is 90 degrees. You have another 90 degrees over here. You have another 90 degrees over here, another 90 degrees over here, and that is basically 90 degrees times 4 is equal to 360 degrees. That is how basically an angle has been defined in terms of degrees. And I don't really know why, but it must have been necessary in mathematics. They have also defined angles in terms of radians. They have also defined angles in terms of, as far as I know, radians and gradients. Gradients are also there. The base for this is, I suppose, something that has to do with either 60 or 66 or something like that. I'm not really familiar with gradients. They have very specific basically applications in basically usually in the kind of basically tools that you see on the sea, on the ships and things like that, something like that, or spacecrafts or something like that. I don't really know much about this one. So radians is basically another way that they have defined an angle. So what they have done is that they have taken a circle, and basically any circle that you draw, you will get some length as the radius of the circle. Now what they have defined, or what they have agreed upon, is that if there is a central angle in this circle, in which case where basically if there is a central angle which is subtended by an arc, which is by an arc on the circumference of the circle, of course, which is equal in length to the radius of the circle. For example, something like this, you can imagine that this curved length is equal in length to the radius of the circle. And so if that is the case, if this length over here, for example, let's call it S, if this length is equal to the radius of the circle, then they have called this angle 1 radian. This is 1 radian. And then in the same way you will get another angle over here, for example, another angle over here. I suppose that one would be this way and this way and this way, something like this. So you get 1, 2, 3, 4, 5. It has to be 6. It has to be around 6 point something. It has to be around 6 point something. So if you do this right, you will get I think 1 radian is around 57 degrees. So it would be something like, for example, let me do this properly. Okay, so somewhere over here, for example, I suppose you could say somewhere over here is 1 radian, meaning that I'm assuming that this length over here, from here all the way up to here, is equal to the radius of the circle. And then you're supposed to get one more angle over here, which is also 1 radian. You're supposed to get one more angle somewhere over here, which is supposed to be 1 radian again. You're supposed to get one more angle over here, so this is 1, 2, 3, 4, 1 radian. And this is 5 and somewhere over here, 5 and 6. So 1, 2, 3, this one is too big. 1, 2, 3, 4, 5 and 6. So suppose that this is also 1 radian, this is also 1 radian, and then this is a fraction of a radian, okay? This is like approximately 0.28 of a radian, of 1 radian. And that is basically why now the way that how basically pi has appeared in here is that the way that pi has appeared in this whole story is that basically you know that if you go one complete revolution all around the circle, the length of that would be the length of the circumference. So that would be the length of the circumference to the length of 2 times the length of the radius. Okay. Now, see, if you basically having this relationship here, we have c to 2r is equal to pi. Okay. So what that means is that the ratio of the circumference to 2 times the radius of the circle is pi. Now now if I multiply this equation, both sides of this equation by 2, I'll get c divided by r is equal to 2 pi. Okay, c divided by r is equal to 2 pi. And that is exactly one complete angle, one complete revolution all around the circle, meaning that now you have basically moved one complete revolution as far as the whole circumference around the circle, and this is your r. So this is the ratio, and this ratio is equal to 2 pi. And then they have called this radian, the radian measure. So what that means is that basically one complete revolution around the circle has been called 2 pi radians. And over here, as we defined basically the 1 radian, we said that the ratio of if the length of this arch s is equal to the radius of the circle, that is considered to be 1 radian, meaning that s is equal to r, or the ratio is equal to 1. Now, if this ratio, basically this c, or the circumference, is the same thing as this arc over here, but now you have gone one full revolution around the circle, and then basically you have the same r over here, so that's basically exactly the same situation. And then what that means is that if you, instead of basically one arc which is exactly the same distance, the same length as the radius of the circle, if you go one complete revolution, that angle is going to, instead of 1 radian, is going to be 2 pi radians. And that is basically how 2 pi, basically pi has been found over here. So what that means is that now this angle, this central angle that we have over here, that starts from here and goes all the way up to here, one complete revolution, is basically the whole circumference of the circle to the radius, and that is basically 2 pi, meaning 2 times basically pi, which is 2 times 3.41415, and so on and so forth, which is the same thing as approximately 6.28. And you see that you get exactly 6. You get exactly 6 radians over here. 1, 2, 3, 1, 2, 3, 4, 5, 6. And then you will get some fraction of a radian over here, which is 0.28. 0.28 of a radian over here. So what that means is that basically then of course, if this angle is 0, and then if you make one full revolution, this becomes 2 pi. Then what that means is that 1/4 of 2 pi is basically pi by 2, 1/2 of 2 pi is pi, and 3/4 of 2 pi is 3 pi by 4, and then basically 1 times 2 pi is then basically 2 pi itself. And that's basically where this number comes from. And this number, what that means is that this pi by 2 is just simply 3.14, for example, approximately 3.14 divided by 2, which is something about 1.5, 1.5, I don't know, 05, and so on and so forth, something like that. So what that means is that, for example, you can see that if I set my calculator to radians, and first of all, if I calculate pi divided by 2, it gives me 1.57. Not 1.505, but 1.5707. I can take this as, for example, 1.5708, for example. Now, if I calculate the sine of pi by 2, the calculator is going to give me 1. The sine of 90 degrees or pi by 2 is 1. I can also say that the sine of 1.5708, that is going to be 0.999999 and so on and so forth, very, very close to 1. So that's basically which what that means is that basically pi by 2 is just simply a rational number, which is just a simple real number. There is nothing special about it. And for the same reason, you can approach this number in the same way that you would approach any other real number, really. Like you want to approach 2, you want to approach 4 from the right and left, and you can do the same thing over here as well. So that is the whole story. Now let's see let's go back and solve this problem as well. Okay, so now in order to find the limit of this function at x is equal to pi, so again we need to do the same thing over here, meaning that the same thing that we did in the case of the other examples, meaning that I can simply create a table of values over here for the input of the function and the output, and call this, for example, x and f of x. And then I can imagine that, for example, this is the point pi by 2, and then I can basically get closer to pi by 2 from the right or from the left. So from the right, for example, you could write pi by 2 plus, for example, 0.01, or you could write pi by 2 plus 0.1, or you can write, for example, pi by 2 minus 0.01, or you can write pi by 2 minus 0.1 minus 0.1 minus 0.1. Now if you give these values to a calculator, because it's not, of course there is no way for me to calculate these values in my head, and it's not even possible to calculate it on a piece of paper. Maybe people used to do that, like, for example, probably 100 years ago or 200 years ago. I would imagine that people, this must have been a skill in some basically necessary skill in mathematics, that you would be, that you were required to calculate these values on paper, because basically there was no calculator. And for the same reason, for example, I have seen all of these books that, for example, back then, I don't really know how long ago, but back then there were all of these charts. Mathematicians and physicists and researchers and students didn't have calculators, so you had to use all of these. There were these very thick big books, and they were full of these charts for different values of for example, the log function, the trigonometric functions and all of these functions, and then you would have to, for example, suppose you wanted to calculate this value, and then you would have to just keep looking like a big dictionary. You would have to keep looking in that book to come to that index, and then go in and find, for example, the value for that, the output value of the function for that input value, and then you could write it down on a piece of paper. It must have been very painful, really, back then. I mean, without a calculator, it's not, I mean, life is really unimaginable. But, well, they basically, they were living in those times, but now we have, I suppose, even these computers are I mean, the computers that I'm using right now, for instance, this is considered to be a classical type of computer. I don't know where my video went. This computer, which is a Intel CPU i7 and RAM, which is so and so and so. So this computer is considered to be a classical computer. And today we have quantum computing. So, well, now anyway, if you give these values to a calculator, what you will get is basically 0.9999, and for this value you'll get the same, for this input you'll get the same value, 0.9999. For this value you'll get 0.9950, and the same value over here, 0.999950. And the reason why you get these values, the same values for basically plus 0.01 and minus 0.01, is that you know that sine is a cyclical function, is a periodic function. And, well, if you have your sine function over here, so basically, for example, the sine of pi by 2 would be this value over here, which is 1. The sine of 90 degrees. This is 90 degrees. But suppose that, for example, pi by 2 plus 0.01 is basically, suppose that it's this value over here, and, well, pi by 2 minus 0.01 is the same angle in the other direction, would be this value over here, and the sine of these two angles is basically the same height on the y-axis, the same height on the y-axis here, and therefore the sine of these two angles is going to be equal. And that's basically why, again, you would get the same sine values for, this angle and for this angle as well, because these two values are the same, and so you have pi by 2 and so on and so forth. So then what that means is that now from this we may deduce that the limit of f of x as x tends to pi by 2 from the left is equal to the limit of f of x as x tends to pi by 2 from the right, and that is equal to the limit of f of x as x tends to pi by 2, and that is equal to 1. And of course this might be also supported by the graph of f of x is equal to sine x, which is given in figure 3.8. So figure 3.8 would be, for example, let's graph y is equal to sine x. So you can see that over here this is pi by 2. Pi by 2 is approximately, you can see this is pi by 2, which is somewhere around 1.6. somewhere around 1.6 is pi by 2, and so you can see that when you get very close to basically this point over here, which is pi by 2, then the function, the value of the function is approaching this value pi by 2 comma 1, and the other side as well, pi by 2 comma 1. So that is basically that. Now the next basic illustration that we have is suppose that you have a function f of x is equal to x plus cos x, and we want to find the limit of f of x as x tends to 0. So of course you know that basically cos of 0, you know that cos of 0 is equal to 0, and then basically if x is equal to 0, so at 0 the value of the function must be 0. But as x tends to 0. So now if we basically prepare a table for this function, if I prepare a table for this function and write this as basically, let's suppose that this is x and this is f of x, and let's say that this is, for example, 0, and you want to get closer to 0 from the right and left, so this is 0.001, this is for example 0.01, and this is for example 0.1, and let's say that this is negative 0.001, this is for example negative 0.01, and this is negative 0.1, and so for example, if you have the cos of this angle over here, it would be very tiny value. Very tiny value would be basically this. Would be basically if this is 0 degrees, or you can take it as 0 radians as well. Of course, I mean I would take it as 0 radians, because most of the time here basically angles are meant to be in radians. So if you take this as 0 radians, then 0.001 would be very tiny, I mean very close to 0. And so it would be very close to 0, of course, and then of course you know that cos of 0 is equal to 1. Cos 0 is actually equal to 1, and cos of pi on the other side is equal to negative 1. So then this value is going to be very close to 1, and then your x at that point is also very close to, basically your x is 0.001, right? So it would be some value, basically you could calculate it this way. For example, you can say that the cos of 0.001, the cos of 0.001 is basically this value over here, which is very close to 1. And if I take this value and add to that 0.001, what I will get is 1.0009995. So that's how you would calculate, for example, this output for the function, and that would be basically 1.0009995. 1.000999995. The next value would be 1.00995. The next value would be 1.0950. The next value would be of course here your x is negative, so it's these values are going to be over here. For example, the cos value would be negative, something around -1, and so you would get basically, so the cos value over here would be something around -1, a little less than -1, a little less than -1, and oh, I'm sorry, no, I made a mistake here. See that this angle over here, -0.001, is not over here, and the cos of that is not -1. That's not true. The cos of this angle over here is basically, this is that if for example, suppose that this is, for example, 30 degrees. So this angle over here would be -30 degrees. So if this angle, for example, over here is 90 degrees, this angle over here would be -90 degrees. Okay, so by the same logic, this angle over here, which is 0.001, very close to 0, this angle over here, if I call this 0.001, for example, radian, then this angle over here, the exact same amount in the other direction, is going to be -0.001 radian. And of course it's going to have the same cos value, because as you know, cos of -x is equal to cos x. The cos of these two angles are going to be the same, because this is the same distance on the x-axis. So then the cos of this angle is going to be the same value as the cos of this angle, but then from that value you just subtract a 1,000th of a unit, and so you're going to end up with, for example, 0.99899995, for example, 0.99899995. Or over here you're going to end up with 1.00 no, 0.9, I'm sorry, you're going to end up with 0.98998995, or over here you're going to end up with 0.9850. Okay, and that is basically that. Now what you can see is that basically the limit of f of x when x tends to 0 from the right, for example, is very close to 1. The limit of f of x when x tends to 0 from the left is very close to 1. So then you could say that the limit of f of x, of course very loosely, but then based on what we are doing right now without any definitions, I could do this, I could say this: the limit of f of x when x tends to 0 from the right is equal to the limit of f of x when x tends to 0 from the left is equal to the limit of f of x when x tends to 0 is equal to 1. And of course there is something interesting here, which based on the previous example, and here you can see the same thing. So you saw over here that the limit of f of x when x tends to 0 is equal to 1, and that is the limit of x plus cos x when x tends to 0. Now, if you calculate the limit of x when x tends to 0, that is going to be equal to 1. The limit of basically, no, I'm sorry, this is equal to 0. The limit of x when x tends to 0 is equal to 0. Now the limit of cos x when x tends to 0 is equal to 1. So you can say that the limit of x plus when x tends to 0 plus the limit of cos x when x tends to 0 is equal to 1 is equal to the limit of x plus cos x when x tends to 0. Which means that the limit of x when x tends to 0 plus the limit of cos x when x tends to 0 is equal to the limit of x plus cos x when x tends to 0. That is basically what we showed in the previous example as well, and this works here as well. Okay, so we have a couple more illustrations here. I'll be right back with the rest of these. Okay, so the next example that we have is, for example, consider the function f of x is equal to 1 over x squared. So if you have f of x is equal to 1 over x squared for x greater than 0, you want to find the limit of f of x as x tends to 0. So basically what you would normally do is basically just prepare a table of the functions, the table of values of this input outputs for this function as x and f of x, and then you are supposed to get close to 0 from both sides, meaning that from the right side and from the left side. But the problem here is that x is supposed to be greater than 0, meaning that negative x's are not a part of the domain of the function. So these parts are not a part of the domain of the function. So you have only these parts over here. So then you can go for example, values like 1, like for example 0.1, like for example 0.01, or and so on and so forth. Now 1 over 1 squared is equal to 1. 1 over 1 squared is equal to 1. Now if you get closer, if you were to get closer, 1 over 0.1 squared is 1 over 0.01, which is equal to 100. This over here is equal to 10,000, and so on and so forth. If you go for example 0.001 over here, you would get 1 million. You would get 1 million over here. So what that means is that, and there is a pattern in these numbers, meaning that 0.1 is 10 raised to the power negative 1. Is 10 raised to the power is basically, you can write this as you can write this as 0.1. You can write it as 1/10, which is the same thing as 1 over 10 raised to the power 1. And over here you have basically 100, which is the same thing as 10 raised to the power 2. So 1 over 10 raised to the power 1, 10 raised to the power 2. Now over here what you have is 0.01, and that is equal to 100th, which is equal to 1 over 10 squared, which is equal to 10 raised to the power negative 2. This is 10 raised to the power negative 1. So, and then over here you have 10,000, which is 10 raised to the power 4. So you see that 10 raised to the power negative 1, 10 raised to the power 2, 10 raised to the power negative 2, 10 raised to the power 4. So you can say that over here you have 10 raised to the power negative n, and over here you have 10 raised to the power 2n. So then you can write 10 raised to the power negative n and 10 raised to the power 2n. What that means is that as you get, and of course I wrote this the other way around. I was supposed to write this to get closer and closer to 0. Basically I was supposed to, these numbers should be actually on the other side, but you get the idea. Meaning that as I'm moving towards the right in these numbers, I'm getting closer and closer to 0 actually. So what that means is that as I'm getting closer and closer to 0, the value of this function is getting larger and larger at a very rapid rate, meaning that when I get very close to 0, the value of the function could be larger than any number possible, meaning that, and larger than any number possible is just simply infinity, positive infinity. So then you can say that mathematically we can say that the limit of f of x is equal to, when x tends to 0, is equal to positive infinity. And of course the same would go for example, if you had the function, for example, f of x is equal to 1 over x, that would also be an example of the same kind of thing, meaning that your function would tend to infinity at x is equal to 1, at x is equal to 0. And in these kinds of functions, usually what happens is that you get basically you get a vertical asymptote in the graph of the function. For example, for this function 1 over x, the graph of the function would be at x is equal to 0. Basically your function would tend to, as you make your x larger and larger, you would have a very small number over here, meaning that the function would be something like this. So in this function you would get basically 2 asymptotes, something like this. So for example, this would be the graph of the function. The graph of the function f of x is equal to 1 over x. Now let me draw the graph of the function over here. 1 over x. You see that the graph of the function has actually these 2 asymptotes. This has actually 2 asymptotes. One of the asymptotes is the x-axis itself, and one of the asymptotes is the y-axis itself. So you would get basically these 2 asymptotes, one horizontal asymptote, one vertical asymptote, and that is basically the graph of the function. Now about f of x is equal to x, f of x is equal to 1 over x, I think the graph of the function is going to be the same thing, meaning that at when you make, if you have f of x is equal to 1 over x squared, then when you make your x basically 1, 2, 3, 4, you have 1 over 4, 1 over 5, 1 over 6, and so on and so forth, and it gets very large very fast, meaning that 1 over 1000 would be some distance very close to the x-axis. So again, you would get some function like this, and another part of the function would be this thing over here, meaning that you see over here, oh okay, so for the negative values over here you'll get of course positive outputs, meaning that this part of the function would also be up here, like this. That is the graph of the function f of x is equal to x squared. You have one horizontal asymptote and one vertical asymptote. So that's basically that. Or as another illustration, let's say that you have for example you have the function f of x is equal to you want to find the limit of f of x when x tends to 0, where f of x is equal to x minus 2 when x is less than 0, is equal to 0 when x is equal to 0, and it's equal to x plus 2 when x is greater than 0. So this function is something like this. So x minus 2 would be this point over this line over here. X minus 2, basically this point over here, and so this would be x minus 2. This is f of x. This is f of x is equal to x minus 2. Now x plus 2 is basically this thing over here. It is basically this function over here. F of x is equal to x plus 2. And of course f of x is equal to 0 is basically this point over here. Now f of x is equal to x minus 2 is for x less than 0. For x less than 0, meaning that only this part of the graph is really required. The other parts are not really important here. So, and for x plus 2, only for x is greater than 0. So this part of the function is not really required. And then what you want to do is basically, and this is only for x, for example over here x minus 2 is only for x less than 0, meaning that at 0 the function is not defined here. At 0 this is not defined there. So you need to basically create these circles over here to indicate that the function is not basically the value of the function at x is equal to 0 is not this point, but this point over here. And that is basically your x, your y, and that's basically the whole story. Now you can see you want to find the limit of the function at x is equal to 0. So you see that if I basically create some values, input outputs for this function at x is equal to, very close to x is equal to 0, and suppose that this is x and f of x, and suppose that this is x is equal to 0, I get close to 0, for example, like 0.001. I have basically 0.01, and I have, for example, 0.1, and the same thing, negative 0.001, and negative 0.01, and negative 0.1, and negative 0.1. Now to find the output of the function for these inputs, you have to use basically this clause over here. You have to use this clause over here, because this is for x's greater than 0, and these are x's greater than 0, which is 2 plus x. So you would get 2.001, 2.01, or 2.1. For x's less than 0, you have to use this clause over here, meaning that x minus 2. So you would get basically negative 2 minus negative 0 minus basically 0.001, which is negative 2.001, negative 2.01, negative 2.1, and so on and so forth. So you see that as x is getting very close to 0 from the right, the limit of the function seems to be 2. As x is getting close to 0 from the left, the limit of the function seems to be negative 2. So then you can write the limit of f of x as x tends to 0 from the right is equal to positive 2, and the limit of f of x when x tends to 0 from the left is equal to negative 2, and these two values are not equal. These two values are not equal. Meaning that the left hand limit and the right hand limit do not coincide, and so you can say that the limit of the function, the limit of the function at x is equal to 0 does not exist. Does not exist. And you need basically one important thing here is that basically the value of the function at x is equal to 0 is actually defined, meaning that you can say that f of 0 is actually equal to 0. So the function is defined at x is equal to 0, but the limit of the function at x is equal to 0 is not defined and does not exist. And so there is one final illustration here that we will do in this video as well, and then we will end this video. And that is basically we want to find the limit of f of x, the limit of f of x as x tends to 1, where basically f of x is equal to x plus 2 for x not equal to 1, and it is equal to 0 for x equal to 1. So what that means is that your function is something like this. X plus 2 is some line like this. This is x plus 2. This is f of x is equal to x plus 2. But this is for all x's except for x is equal to 1. That means that at this point, your function is not defined at this point, but basically at x is equal to 1, the value of the function is 0. Okay, for x is equal to 1, the value of the function is 0, meaning that the function basically is defined here. And basically that is your function. Now, you want to find the limit of this function when x tends to 1. Now, when x tends to 1, the value of this function, as you can see, is 0. But the limit of the function, which is the expected value for the output of the function at that input, is actually x is equal to basically x plus 2, which is 3. So you can see that the limit of f of x when x tends to 1 is actually equal to 3, and that is equal to actually f of 1, meaning that the limit of f of x when x tends to a again is equal to f of a. And how you can come to this conclusion is basically simple. You can prepare a table of values for this function. You can basically prepare x and f of x over here, and over here what you have is basically you want to know what's happening at x is equal to 1. So on the right side you will have, for example, 1.001 or 1.01 or 1.1. On the left side you have, for example, 0.999, or you have 0.99, or you have 0.9. And the values for this are basically everywhere, basically, except for one. You can use this rule over here, x plus 2, so that would be 3.001, 3.01, and 3.1. Over here, 2.999, 2.99, and 2.9. So you can see that as you're getting close to 1 from the right, the value of the function seems to be very close to 3. So over here your limit is 3. And from the left, you're again getting very close to 3. So then you can say that the limit of f of x when x tends to 1 from the right is equal to the limit of f of x when x tends to 1 from the left, and that is equal to the limit of f of x when x tends to 1, which is equal to 3. And of course, if you basically take a look at the graph of the function, you can see the same thing over here, because the function from both sides is approaching this point, which is 1, 3. And again, over here you can see that basically the limit of f of x when x tends to a is equal to f of a, although no, this is not right. This is not right. I'm sorry. The limit of, basically you can see that over here f of a, which is equal to f of 1, is equal to 0, but the limit of f of x as x tends to 1 is equal to 3, meaning that the limit of f of x as x tends to 1 is not equal to f of 1. Okay, so in some cases basically this relationship was actually the case, but here the relationship is actually not the case. It's not true. So Note that in general, at any given point, the value of the function and its limit may be different even when both are defined. So that's basically the case over here. Now, in the next video, we will talk a little bit about algebra of limits. And then we have a couple more things about limits of polynomials, rational functions, and so on and so forth. And then we will connect the whole thing to the concept of derivatives. So I will see you in the next video. Thank you.